So now, as I'm doing these problems, I didn't work them out beforehand. So I think the process is right. But if the numbers are a little bit funny, it's probably because we're making the mistake, right? We're making the mistake. We just got to make sure Limbo stays in the room here. So now let's go back to this. So what we want to do here is we want to calculate this voltage. Now when I look at this voltage here, probably the one thing that you want to pay attention to, you got to look at that source. Where is the UT attached to? That's 6 e to the minus t. So we can see that if I talk about the source, at t equal to 0 minus, we see that the source is only equal to 3 volts. But at t equal to 0 plus, that source now becomes 3 plus 6 e to the minus t. I've seen too many people just say, oh, there's no source at t equal to 0 minus. Not true, right? So you want to pay attention to that, to these little details. So if I want to calculate this, as always, I got to calculate this voltage DC. But the problem is that you can see that this is a time-dependent source. So what we have here is that we have a time-dependent source. So that means I got to derive the first order equation. And I'm going to say this because I saw this on the quiz. They'll go in here and they'll go like, oh, I know what these. I just got to go calculate this guy. Right? Because we're talking about a capacitor here. The problem is, this is not valid. It's not valid because I don't have a constant source at 0 plus. Right? Not valid. Now note, some of you are actually deriving, even for constant sources, the differential equation. And that's totally legit. In fact, that's probably the most common that I see in textbooks. Why do I use this? Because I think it's physical. I think that you're really looking at where did the circuit start at, where does it go to, and how does it do that? That's why I prefer this way than not just starting with differential equations right away. But here we have no choice. So let's write down the equation. So what I'm seeing here, since these two are in series, the current through this resistor must be the same as that resistor, so I'm going to treat them as the same. So if I look at this thing here, I can do a KVL all the way around, but what I'm thinking here is that I'm going to just draw in my nodes right now, just to make sure that we're really clear. So if I draw in my nodes, what I'm looking at is that I'm looking at t equals to 0 plus. So that means I got a source. So I'm going to combine these two resistors like this here. So I'm going to get 3 plus 6 e to the minus t. Then I'm going to have a 4 ohm resistor. I'm going to have an 8 ohm resistor. And then I have my cap. So I have H. Then I got C here, which is 3/16 farad. So if I look at this, if I put my ground right here, you can see right away that this is Vs. This is Vc. So what I'm going to do here is I think I'm going to apply KCL. I think I can do KVL, but in my mind, I'm seeing KCL as the easy one. Because if I know that current, I know this current, and of course I know that current right there. So I'm going to apply KCL to do this one.
What made you want to take that 2 ohm from the bottom and combine it with the top?
Because they're in series. And I know that the current through this resistor must be the same as that. And so if I want to calculate that voltage, then all I need is the current through the 4 ohm resistor to get that voltage and then multiply it by 2.
Okay.
In fact, that's the solution right there. In the end, when we go to solve the circuit problem, we just got to calculate the current here in order to get the voltage there. So then I'm going to apply KCL. So if I apply KCL, you could see that the current of the 4 ohm must be the current of the 8 plus the current of the cap. So if I look at the 4 ohm, well look, there's the voltage right across this guy. So that guy has to be Vs minus Vc divided by 4. And this guy, you could see, is just Vc. So then I'm going to write Vc over 8 plus Vc. Plus IC, excuse me. So what I'm going to do now is I'm going to bring this guy over. Look at, I got my differential equation right away. So if I look at this guy, what am I going to do? So I'm going to write this as a quarter V source equals this guy. Now let's add, I'm going to add Vc here. So if I bring this Vc over, I got Vc over 4. And then I have what? A fourth plus an eighth. That should give me 8/3. Yeah, 3. Sorry about that. I don't know what that. I think I'm thinking resistance. So I'm going to get Vc, and then this guy tells me that it's got to be. I think that's a 16, right? That is a 16. So then I get 316 S hat Vc. Damn, I keep forgetting that 16 here. So now what am I going to do? I'm going to clean it up now. If I clean this guy up here, I'm going to multiply everything by 16.
It's 3/8, right? VC.
Tell me how am I getting, isn't it C times the derivative of VC to get the current?
Yeah, but they're talking about where you have 3 VC, it should be 3/8 VC.
1/4 VC and add an actual 1/8 VC, so it should be 3/8.
3/8. Oh, thank you. Absolutely right. So then if I multiply everything out through this thing here, I should get S hat VC. Then I'm going to get what? 16 over 8, which should give me 2. And then on this side here, I should get 16 over 3 divided by 4 should give me 4/3. So if I get 4/3, then I'm going to bring this guy in here. So then I'm going to get 3 plus 6 e to the minus t, which will give me 4 plus 8 e to the minus t. Right? I think that's clean. Dude, you gotta get this right. Right? You get this wrong, you're solving a different circuit as far as I'm concerned. So this is the one where you're going to be sweating. You should be sweating, going like, did I get this right? Okay, did I get this right? Your ass better get that right. That's all I know. So then, I'm going to just do a small check. Remember, this does not guarantee that you have the right solution here. Right? The right differential equation. So what this tells me here is that at t equal to infinity, I should get Vc at infinity should be this B constant. And if I look at my equation, it tells me what? It tells me that this guy here, that's the one thing that we want to check. So if I plug this guy in here, I'm going to get what? S hat times B, which is 0, plus 2B equals 4, and then this guy should be 0 at t equal to infinity. So immediately that tells me that B should give me a value of 2 volts. The question is, what does the circuit say? Okay? What does the circuit say? I'm going to go back to the circuit now. When I go back to the circuit, what I'm seeing here is that this guy dies off. This guy's an open. So then, as I go along here, that means that the voltage across this guy must be the same as the V8. So that tells me here, V8 at infinity must be the same as VC at infinity. So if I look at this here, then I got 3 going into what? 4 and 8. It's dividing these guys. So then this should be 8 over 4 plus 8 times 3. Oh, I thought I was off there for a minute. So they match up. That gives me a little breathing room. Okay? So these guys match up. So now, let's go calculate the solution. So what we want to do now is that now we want to calculate the general response. Okay, so if I go to calculate the general response, I'm going to look at my differential equation. Right? My differential equation says that I got to have, let's say, B1 and a B2. And then the natural response forces me to have an A constant. So here we go. So that means here that the voltage of the cap should have a natural response and a forced response. So the natural response should be what? A, E, and then it's minus T over tau. I look at my equation and I say, what is 1 over tau? I just pick it off. It's this guy right here. Right? So then I write minus 2T. There's my natural response. Now, I got to get my forced response. The fact that I have a constant and an exponential means it's got to be B1, B2, e to the minus t. So now my job is to get what? B1 and B2. So now we need to determine B1 and B2. So the way I do that is I take my force response, right? This is my force response. I take this and I plug it back into the differential equation. And then I force B1 and B2 to match these guys right here. So let's do that. So now I have S hat VC force plus 2BF has to equal 4 plus 8 e to the minus t. So now I'm going to plug in B1 plus B2 e to the minus t. Okay? So if I plug this in, I'm going to take the derivative of this guy. When I take the derivative of this guy, that guy's a constant, so it's 0. I take the derivative of this, the minus sign comes down, so I get 0 minus B2 e to the minus t. Plus 2 times this response, so I'm going to multiply this by 2, so I should get 2B1 plus 2B2 e to the minus t, and this guy has to equal 4 plus 8 e to the minus t. Okay, so these numbers are nice, because if you look at this, 2B1 has to equal 4, so that tells me that 2B1 has to equal 4, tells me that B1 must be 2. So when I look at this guy, you can see that I got minus B2 plus 2B2, so clearly that's just B2. So I got B2, this guy, so then I'm going to get B2 e to the minus t must equal 8 e to the minus t, which tells me that B2 must be 8. Yes?
We've gotten the B1 just from T of infinity. Very quickly.
Okay. So we could have done that. Okay. We totally could have done that. I totally would have worked. I'm just a little bit slower than you are. See, that's what happens as you get older. Now, to be honest, I'm expecting that you guys are actually better at circuits than I am almost at this point. I'm a little bit more polished because I got 40 years on you guys, but I expect you guys to be faster than me and better than me. And you know what? I think that's a high compliment. So then, let's go on. So if I look at the general response, right, so now I got dc of t gives me a e to the minus 2t. I plug in these guys, so I get 2 plus 8 e to the minus t, right? So you can see I only have one thing left. What do I got to do? I got to calculate that guy right there. So now my job here is that I got to determine the initial condition and apply it to to get A. Right? Note that this is the exact same process as the second order differential equation. Okay, the second order differential equation, of course, is messier. But here we go. So now I'm going to look at t equal to 0 minus. Okay, at t equal to 0 minus, I'm going to redraw my circuit here, and it should be what? I got to be careful here because remember, at t 0 minus, it's 3 volts. So now I'm going to come in here and I have 3 volts, and then I have a 4 ohm, I have an 8 ohm, and then I have VC minus. Yeah. Once again, we know that it's, did we do this already? No, okay. So if I do this here, I can see that the voltage 0 minus implies that it has to be the voltage across the 8 ohm resistor at 0 minus. So it has to be what? 8, 4 plus 8 times 3, which gives me what? I'm going to get, right, that's the same as, well, that's got to be 3/4, so it's got to be what? But 8 over 12 is 2/3. 2/3 then gives me 2. Right?
It's the same as at infinity.
Right? Which is the same as the infinity. That's what I'm saying then. Did we do this already? We sure did, right here. But when we went and did this check, this is the exact same thing that we did. So that means it's going to start, and then it has to jump back to its original value. So then I have VC of 0 minus. So that being said here, now I'm going to apply this condition to this guy. So now applying VC of 0 minus to get A, we then say that VC of 0 minus, which is 2, which is the same as A e to the 0, which is 1, plus 2 plus 8. So if I have that equal to 2, you can see that this 2 and this 2 cancel out, so then A has to be negative 8. So this implies here that A has to be negative 8 volts. So now I have my complete response. So the complete response to that source is VC of t is going to be minus 8 e to the minus 2t plus 2 plus 8 e to the minus t volts. So now I have the complete response. So now I'm going to use this to calculate the voltage here. Now, I kind of hinted that it had to be that solution right there. Right? It had to be that equation. So when we come back, if I know to get this current, I need that current and that current. Right? That's one way that you could do that. But damn, that's got to be messy as shit. Right? You got to get the current of the 8, then you got to get the current of this, which then you got to multiply this by VC times that, and then you got to get IC, and you got to take the derivative, and then you got all this crap. Or you could use KVL. Right? Do I know the source? Yes. Do I know the voltage? Yes. Yeah. Do not do it this way. This is suicide. Right? That's suicide. You will not have time on your exam. And as you can probably imagine, I'm in a very difficult position of writing a fair exam for the amount of time that we have. Right? One mistake on my circuit, that circuit may take you the whole exam. So I got to be really careful. Okay? So what I'm going to do now is that I'm going to solve for the voltage V2 ohm of T. Okay? So what I'm going to do here is that you can see that I know that voltage. Right? I know that voltage. So I can see here that the voltage of the 4 ohm has to be Vs minus Vc. But note, this guy is dividing the voltage across these two resistors right here, right? So that means that V2 has to be half of that voltage. So this implies here that the voltage that we're after is half of V source minus Vc. So then I just start plugging it in. So if I start writing this in here, I'm going to get 1/2. Where's my source? Right here. So I'm going to write 3 plus 6 e to the minus t. And then I get this term that I got to add. So it's got to be minus minus, so I got to be careful here. So the first term is positive, so I'm going to get 8 e to the minus 2t. And then I got two negative terms, which will be minus 2 minus 8 e to the minus t. And so that gives me the voltage here. So what I'm seeing here, that I'm going to get what? 3 minus 2 gives me 1. So this guy has to go to 1/2. And then I'm going to get, and then if I add these two together, right, I should have been careful here. Right, so 1 slash of the purple tells me the constant. Double underscore is going to give me these guys right here. And so this gives me 6 minus 8, so I should get minus 2 e to the minus t. And then this guy's, oops, I got to divide by 2 though. Right, then I divide by 2, and then this guy divided by 2 gives me plus 8, oops, plus 4 e to the minus 2t. So then this is the voltage of the 2 ohm for t greater than 0 in units of volts. So now, does that make sense? What did we say? Vc at t infinity, we would expect this guy. So if I look at the circuit here, what do I know? So let's plot this guy. Initially, this is 2 volts, right? This is 2 volts. Maybe I'm making too many steps. Let's see if we can do this without rewriting it. At t infinity, we agree that this guy's gone. This guy's in open, and we already calculated that this was 2 volts. So if I do a KVL around like this here, if this is 3 and that's 2, that has to be 1 volt. Right? So if I look at the circuit here, what we're seeing here is that at t equal to infinity, we're seeing here that the voltage across the 4 ohm has to be 2 volts, which then implies that the voltage, oops, I said 1 volt, that the voltage across the 2 ohm resistor must be half a volt. So when I look at this guy, you can see that at t equal to infinity, that term drops out, that term drops out. That's good. So we know it's got to go to half a volt. The question is, what is it at t equal to 0? So at t equal to 0, note that this is 4, and then that's a half, so that's 4.5, and then I'm going to subtract 1, so that gives me 3.5. So at t equal to 0, what we're seeing that this guy is at 3.5 volts. And what's it going to decay to? It's got to decay to 1/2. So you can see here that let's make this value here the 1/2, so the voltage equal to 1/2 volt. So we see that this guy has to decay down to this value right there. What is V2 at 0 minus? It has to be exactly the same thing, right? At t infinity that's there, but at 0 minus that's not there either. So that means that this guy comes in and it does what? It comes in at half a volt for V2 at 0 minus, and then it jumps up to there. There's a discontinuity And then I get that behavior right there. So this exponential, what did it do? It gave it a pulse. And then as soon as that pulse decays, it goes right back to where it started at.